Hello, hello, hello. This is Nicholas on this lovely Saturday evening, talking to you today about a couple of things that we usually take for granted with the vector cross product. And usually we take them just in faith and without proof. So I'd like to give some geometric and intuitive proofs for these facts. The first fact is that V cross W, so if we've got two vectors, V cross W is perpendicular to V and it's perpendicular to W. They're all, V cross W is perpendicular to both of those vectors. Now, we usually don't see a proof of this, and a teacher tells us, and we just assume it to be so. So if V cross W is perpendicular to, say, V, then that means that V cross W, I will say V dot V cross W has to be equal to 0. And there are two ways to think about that fact. The one fact being straight from the definition of the dot product, which is V dot W is equal to magnitude V magnitude W cosine theta. And that's fine, because then realize that if any dot product is 0, that means that this cosine theta is 0, which means that theta is 90. Now, I personally don't think of it like this. I think of it that, well, conceptually, what is the dot product? And I do have a video on this, but conceptually, the dot product measures how much two vectors lie in the same general direction. Now, if they're perpendicular to one another, it ought to be so that their dot product is 0. That's the intuitive sense of what a vector dot product even is. It's a scalar that kind of tells you how close two vectors are to each other in the same direction. That's why if you've got a vector dotted with itself, it's just the magnitude of that vector squared. Because if you dot a vector with itself, that's the most it's ever going to be in the same direction of itself, right? If you've got two vectors lying on top of each other, that's the maximum possible togetherness that you're going to have with the vectors. So now, and you can actually just compute this dot product using just straightforward algebra. But geometrically, what is this saying? Well, it's saying that if we are to imagine this dot product, we can think V dot V cross W as a matrix, and it's going to be defined by, let me erase the 0 here, the vectors V, V, and W, right? And they're going to have components. We don't know what they are, but that doesn't really matter. So that's why I've drawn the dashes there to represent the components. Now, we have a 3x3 matrix, which represents a parallel pipette spanned by the vectors. And if you're not familiar with this fact, I have plenty of videos on it. But so parallel pipette, let's say we've got V, W, V cross W would be perpendicular to those. And so we have this 3D, doing my best to draw it, we have this 3D shape that's spanned by those vectors. But realize, though, that if we have this parallel pipette defined by 3 vectors, and 2 of those vectors are the same, then that means it's a degenerate parallel pipette that can be reduced to a 2D parallelogram given by, say, V and W. And so this would be the parallelogram in question. Now, the determinant gives the volume of that parallel pipette. So what that would mean is that, of course, this dot product is 0 because the volume of the parallel pipette is 0. And so what that tells you is that V is perpendicular to V cross W. And likewise, you could have put W for here, and you would have got 2 W's and 1 V. Now, the next thing I want to show is that V cross W, the magnitude of it, V cross W, is equal to, and I usually write it like this, the area of the parallelogram. That's why I draw these 2 parallel lines here, they're a parallelogram. The area of the parallelogram spanned by V and W. And I drew that before the parallelogram spanned by V and W, right? It would look something like that, V and W. Okay, so what I'm going to do here is I'm going to consider V cross W with itself, okay? So what I'm going to do is I'm going to think about V cross W, and that's going to be dotted with itself, V cross W. So V dot W cross V dot W. Now, we can think of this as the determinant of a matrix where the rows are defined by the vectors. So it would be like this. They're defined by the vectors. V cross W on the first one, V on the second one, and W on the third one. And then they have components, of course, but we don't really know what they are, and we don't really care what they are. And so now, realize also that any vector dotted with itself is just the magnitude of that vector squared. So this is also equal to the magnitude of V cross W squared. Okay. And now realize also that this is a determinant, and it's the determinant of the three vectors, V cross W, V, and W. And so that means, and you can look at my videos on what the determinant of a matrix actually means, but it's a scaling factor that space undergoes in the linear transformation represented by the matrix. And so this determinant here would be equal to the volume of the parallel pipette spanned by V cross W, V, and W. And this is equal to the magnitude of V cross W squared. Now, of course, the volume of a parallel pipette is equal to the area of its base times its height. So what that means is that the volume here we could rewrite as the area, the parallel pipette of the parallelogram spanned by V and W, times its height, should be the magnitude of V cross W, is equal to the magnitude of V cross W squared. And look at that, we can just cancel out one of those factors, and we get that the magnitude of V cross W is indeed the area of the parallelogram spanned between V and W. And that's a pretty nifty fact. One thing that you can also use it for is to note that the area of the triangle spanned by V and W. So we have a parallelogram here, but it can of course be broken up into a triangle like this. This area of the triangle would be 1/2 magnitude V cross W, because it's just half of a parallelogram. And I guess one other thing that I would like to mention is the actual formula itself for the dot product. Now, we can use the cosine rule here because it's going to work out nicely. So let's imagine that we have, actually let's not even think of a coordinate system. Let's just say we've got V and W here. Okay, and they make an angle theta with one another. This is V, this is W. Now, what would this vector be here? Well, it would be what you would have to add to W to get V. What do you have to add to W to get V? V minus W, of course. So that's that vector right there. Now, we have a triangle here. And let's use the law of cosines on it. So we would get that the magnitude of V minus W squared is equal to magnitude V minus magnitude W. V squared minus, V squared plus W squared minus 2 magnitude V magnitude W cosine theta. Okay, and now what we can realize is that V minus W, the magnitude of V minus W squared represents that vector dotted with itself. It represents v minus w dot v minus w. And I'm not going to write the whole left side again. But now remember that the dot product is distributive. So let's just FOIL this out, right? So we get v dot v, which is the magnitude of v squared, minus v dot w minus w dot v, and the dot product is commutative, of course, so that's also the same as minus v dot w. And then we get negative w dot negative w, which is plus magnitude of w squared. And so now, this is equal to this, and so that means we can get rid of magnitude v squared, magnitude w squared, and now we have left that negative 2 magnitude v, magnitude w, cosine theta is equal to negative 2 v dot w. And voila, v dot w is equal to magnitude v, magnitude w, cosine theta. And so these are definitions that we all just kind of take for granted with the dot product and the cross product. Now, one other thing I guess I would like to mention is that this cosine theta here, why is it important? Well, the cosine in general measures how together two things are, right? So if I've got v here and then w here, and say these are at a 45, then cosine theta will be root 2 over 2 in that case. If I have v here and w here, then cosine theta, cosine 90 is 0. And that's just because of the general shape of the cosine graph, right? It starts at 1 and then goes down to 0. And that it is confirming to the fact that when two vectors are lying on top of each other, you get maximum togetherness. And then the sign is opposite, right? It's a phase shift of 90 degrees. Oops. So that means that right at 90 degrees is when you'd get the maximum magnitude of the cross product. And I guess one other thing to mention too is that this implies that v dot w has to be the magnitude of it. V dot w has to be less than or equal to the product of the magnitudes of the individual vectors. And this is what's known as the Cauchy-Schwarz inequality. And it's used throughout, there's a more general version of it, but this is used across a number of competition math problems and all sorts of fields. And it should really just kind of make sense intuitively. The dot product can only be, the magnitude of it can only be at most the product of the individual magnitudes of the vectors, right? If the dot product measures how together two vectors are, then you can only get you can only get when these two are equal in the case when you have the same vector. You have the same one vector lying on top of another, so the dot product is at a maximum. And I believe we're done.